Hello. Today I will be talking about 2D Maxima finding algorithms, and in particular a certain approach which I have just re-implemented and made available in Python. So I haven't invented this approach. It's a re-implementation from the same algorithm implemented in Fiji ImageJ, which is a software for image analysis, but it's particularly useful and particularly powerful. So I decided to re-implement it in Python and make it available using the package manager pip. So this video is going to describe how this algorithm works, and we'll discuss Maxima Finding in general. So in an image like this, we'd want to find the bright blobs essentially, and a Maxima Finding algorithm, or peak finding as it's sometimes known, is a good choice for finding bright spots or foci which are densely packed and close to one another, and also where there's a variable background. In contrast to, say, histogram-based thresholding, which could also be used to do this, fine maxima algorithms generally focus on finding peaks of intensity in dense areas, whereas fresh histogram-based thresholding can sometimes not work so well when you've got dense packing and there is no clear border separating instances, for example. So there's a sort of niche where you have quite potentially noisy data, densely packed, and where there's a variable background. Okay, these images that I'm using are actually simulated, and the reference in the bottom right hand corner is the source of these particular images. So when thinking about maxima finding, peak finding, it can often be useful to think of your image not just as a 2D grayscale image, but as a topography where bright intensities can be thought of as peaks in a kind of landscape. And this 3D render hopefully shows you this. So we are interested in finding the peaks or the maxima within an image like this, and I've marked them with crosses to indicate that. So going back to our image, what first thing that we'll do is apply a maximum filter. So this is a multi-stage approach, and the maximum filter is kind of quite a conventional filter to apply in the beginning of a sort of fine maxima pipeline. So what this will do is it will find all of the local maxima in the image. So this will look something like this, and you can see they're very densely packed in. Now it has identified the sort of main areas of intensity, and that's a good start, but you can also see it's also found it's highlighted a lot of background intensity. Now this, in theory, these do represent maxima, they represent the local maxima. So within their environment, each of these crosses represents the sort of local peak, as in this is an area where the intensity is higher than the surrounding. But as you can see, this wouldn't be potentially useful because although it's found the main kind of bright maxima, it's also found all of these sub-maxima as well. So we need to do some kind of pruning to reduce these lists of candidates to the more meaningful peaks in terms of what we're after. And so what we're going to do then to do this is some maxima pruning, and this will search for all of those peaks and find certain peaks which fulfill certain criteria of our choosing. So in maxima finding, we're not interested in just the global maxima, that would just give us one peak, and also we're not interested in all the local maxima, because as you could see, based on how we did it, we got many potential candidates. So we want something in between, a sort of not global but not local approach. And so our maxima pruning algorithm will achieve that for us. So I'll go into more of the maxima pruning later, but first of all, I'll talk about how the maximum filter works, because in itself it's quite a useful thing. So at this point, we'll stop thinking about our image as an overall image, and we'll think about it in terms of pixels, individual pixels with a certain value. And what we're going to do is we're going to apply a maximum filter to this. So this is a sliding window based filter, and we're going to use a 3x3 window size, 3x3 pixels. This is very standard for a maximum filter. You can make it bigger, as well, but there's not much gain to doing that when we're going to do pruning afterwards. So a maximum filter is a non-linear filter. It's non-reversible, and also you can't draw the weights of it like you might a convolution kernel. Essentially, what it does is in each area, and I'll show you this in the next few slides as well, it calculates the maximum pixel and retains that as the output. So it doesn't have a particular set of weights which you can just visualize. So taking our region, what we do is we pass our filter window over it, and what we record as our output, which is also visualized in the top right of this slide, we calculate the maximum pixel within our window and use that as the output. So we're going to start moving our window around, and you can see in the output that whatever the maximum pixel happens to be in that 3x3 grid gets retained and produced as the output. So we go through, and what this does is it essentially denoises our image, just revealing the maximum value in each location. And what we get from that is a sort of maximum filter output that looks like this on the right, which is a denoised version of the input image. It's not very useful in itself for what we're doing, but what you do is you compare the pixel intensities in your input to your output, and where they're the same, this indicates a local maxima in a certain way in which we've been able to identify the local maxima, because where they're the same, this means that the output and the input are essentially localized in the same place. So that pixel must represent a local maxima. And this is quite an effective way of sort of dismissing pixels which are on a gradient, because if they're on a gradient, they will not be a maxima. So it will reveal those pixels which are on the top of the sort of intensity range in an area. Okay, so that gives us, as I showed before, our local maxima, but this, because it's not good at determining what are subtle versus quite large peaks, gives us many outputs. So what we're going to do now is we're going to develop, we're going to prune our image just to return our sort of maxima of interest. Now this can be achieved in many ways. Because of the options, they can be varied, and this could be done in a variety of approaches. So what I'm talking about today is just one particular way of doing it, which I found to be very effective, and it only has one parameter. So what we do is we set this noise tolerance parameter, and this allows us to make decisions about which of our peaks we're going to keep and which we're going to throw away. So I'll describe how the algorithm works first through words, and then I will take you through it a bit more diagrammatically. So what we do is we've got all of our prospective peaks from our maximum filter and our local maxima detection. And then what we do is we take our most intense peak first and work down them in terms of intensity. But we start with our brightest peak, and then we are going to look at the neighboring pixels within the certain noise tolerance. So expand out in a sort of flood fill mechanic. And we scan all of the pixels within this tolerance. So if our peak had a intensity of 90, then we'd scan all of the pixels connected to that peak within 30. If our peak is 90 and our noise tolerance is 30, we basically go down to 60 in terms of intensity. So that's our 30 to our 90 minus our 30. And what we do is if the pixels are equal to the maximum, we mark them as equal. If a greater maxima is met, so as we're expanding out, if we enter a region that has been done before and we find it to be larger, then we ignore this active maxima, we cancel it out. If the pixels are less than the maxima but greater than the maximum minus the noise tolerance, so that would be 60 if our noise tolerance was 30 and our peak was 90, we mark it as listed. Then from these listed pixels we make a decision. If we've gone through them and we found that our region is a valid peak region that doesn't connect to a larger maxima, then we mark them as processed. Otherwise, as we mentioned, we cancel them and return them to unprocessed. So from the regions containing a peak, we calculate the best pixel to be considered as a maxima based on minimum distance calculation with all those maxima considered equal. So say we've got a bit of a plateau, then essentially we take the middle of that plateau. Okay, so that's the description of it, but it always helps to see it sort of in action. So imagine we've got a region here with all these prospective peaks, and then we draw a chord across those peaks, that's the blue dashed line. We'd end up with something that like we have on the right. Now, assuming a noise tolerance of 30, we would start with the brightest peak, and then we make a calculation and we look at all of those pixels within 30 of that noise tolerance, so anything above 90 which is connected. And you can see that there is another peak actually included, a sub peak included in that. So what we do is we immediately get rid of that, and that would then be clarified as being a peak centered on the X that we've retained, and we mark all of those pixels as being processed. Now we've got another peak here, an independent one, which we now come to. And if we start, it has an intensity of 100, and if we take 30 off that, our noise tolerance, then we can see that we go below that valley in between this peak and the previous one. And so that's what I've indicated with the blue there. And you can see once it goes into that region, it will also become cancelled out, like so. So from this region, we'd only be left with one peak. Now, if that particular peak, the 100 intensity peak, had been higher and the valley had stayed in the same place, if it had been, say, 120, then that peak would not have merged with the other one, because the noise tolerance wouldn't have sort of leaked the pixels into the other region. So you can see that it's really good at separating things that are quite close to one another spatially, but they have to have a certain distance in terms of the intensity. So if you have sharp peaks, then they will be separated, but if they are kind of sub peaks of one larger peak, then they get amalgamated or forgotten. So that's basically how it works. It's quite a simple mechanic, which clarifies with a little bit of thought, but it's very powerful, and I've used it many times, and I hope that the Python variant will also prove successful. So yes, this would be what we would be left with ultimately from that region. Now, I mentioned the noise tolerance parameter, and just to sort of make clear, if we've got a region with many maxima, then a lone noise tolerance won't do much to it, as in this image. But as we raise the noise tolerance, you'll find that more and more of these peaks get removed, and you're only left with the most dramatic ones left. Okay, so that's the one parameter. And if you were doing an experiment, ideally, you would keep this noise tolerance parameter the same for all of your images as you process them. You could vary it, but you'd have to be careful about how you construct your experiment and how you base that decision, because you don't want to bias it towards one or more outcome. So ideally, you keep the parameter the same once you've sort of worked out what works well for identifying your feature of interest. Okay, so just to summarize, this Maxima Finding pipeline works in 2D, and it involves a maximum filter and a maximum pruning step, and then you get essentially the coordinates of your output peaks returned to you. And the Python implementation, which I will link to below, is pretty standard to use, but I will also create a video where I just live code it and show you how to do it step by step on some example images. So I'll link to that, but please keep an eye open for it too. Okay, thank you very much. If you enjoyed this, please like the video and also subscribe. Thank you very much.